All right, let's look at number 5. It says a student performs an experiment to determine the enthalpy of combustion of C3H7OH, which combusts in oxygen according to the equation above. The student heats a sample of water by burning some of the sample, as represented below. The alcohol burner uses a wick to draw liquid up into the flame. The mass that's combusted is determined by weighing the alcohol burner before and after combustion, which makes sense. Okay, so it gives you that data there, and it says calculate the magnitude of heat in kilojoules absorbed by the water. Okay, so you're going to be using your Q equals MC delta T. Okay, we know the mass of the water, we know the specific heat of water, and we know its change in temperature, right? It would be final minus initial. So that's a pretty easy calculation. Make sure that you convert it into kilojoules though, so you get 1 point for that. Remember, you're not going to add the mass of the water plus the mass of the 2-propanol, and that's because they remain separate. The only time you combine the two masses together or add them together is when you actually mix two compounds together, and as they release heat, they're dissolving in each other. In that case, you would add their masses together. Based on the experimental data, if 1 mole is combusted, how much heat is released? All right? So I would do this problem slightly differently from what they did. I would start off with the 15.2 kilojoules, which is given to you, and then I would divide that by the mass that is actually burned, which would be the 0.55 grams. And that way I'd be in kilojoules per gram. Then I could get out of kilojoules per gram and get into kilojoules per mole by multiplying by the molar mass. Okay? Now that I'm in kilojoules per mole, then I can simply say that would be kilojoules per mole, and that's my answer. Okay? They start with 1 mole of your compound. That works as well. I just think it makes more sense to go from kilojoules per gram and then get into kilojoules per mole. So that's your answer. So 1 point is earned for getting the correct answer, and 1 point is earned for reporting to the correct number of significant figures. So there, that one problem right there is where you got 1 point for sig figs, and that is it. So if you use 2 sig figs there, awesome, you're done. You don't have to worry about sig figs. But we never know what problem you're going to have to concern yourself with significant figures on. All right? So I personally would do 15.2 kilojoules divided by grams and then get into kilojoules per mole, and that would be your answer. That's what we did in class, but they did it slightly differently. Okay? In C, it says a second student performs the experiment using the same mass of water as at the same initial temperature. However, the student uses an alcohol burner that contains C3H7OH liquid that is contaminated with water, which is miscible, meaning it can be dissolved with that alcohol. The difference in mass of the alcohol burner before and after the combustion in this experiment is also 0.55 grams. So that's what the change in heat is. Would the final temperature of the water heated by the alcohol burner be greater than, less than, or equal to the final temperature of the water in the beaker for the first experiment? So let's think this through. Okay? So let's think about this. If you have a contamination of water, okay, what that means is that 0.55 grams of your alcohol isn't actually being burned. Instead, you're losing some water as well, which means that the amount of heat that that water is going to absorb in that sample is actually going to be less. So the final temperature measured is going to be less than that for the first, simply because the second experimenter is combusting less alcohol than the first experimenter. All right? So these are some questions that we've seen in lab and I've been asking you to do. Just get comfortable with doing that reasoning, being like, all right, so since there's water in there, that means that actually less alcohol is going to actually be able to combust, which means that less heat's going to be released, which means that less heat's going to be absorbed by the water, which means the final temperature is going to be less.